Okay, so inverse trig highlights is what I've called this. Arc sine operates on what? Ratio and gives an angle. So cosine inverse operates on and gives. Tangent operates on angle and gives ratio. Okay. So if I have inverse tan of x, is x an angle or a ratio? Ratio. So the output inverse tan of x is what? An angle. Okay. So if I look at tangent theta equals x over 1, I could fill this in. So I would put the x here and the 1 here. Check me. Is that right for tangent? Okay, and what would the hypotenuse then be? Square root of not x plus 1. X squared plus 1 squared, which we can just write as x squared plus 1, right? Okay. Now, when you think about, when you learned, went back to your inverse trig, I guess probably the first week of Cal 1. Oh, I keep hitting that button. We only looked in certain quadrants. Do you remember what quadrants we looked at for inverse tan? It's 1 and 4. Okay, ACTS, because we want where tangent is positive and where it's negative. We're always going to use quadrant 1. Okay, actually, in this case, we could, if you just looked at just using reason, it could be quadrant 2 or quadrant 4. But if you think about the graph of tangent, there are natural breaks. If you cut along the dotted lines, those are natural breaks, the asymptotes. So we actually cut and look at negative pi over 2 to pi over 2, right? Do you remember that from your review of inverse trig? I will post an entire video over this that if this is not that solid for you, you need to watch the entire old lecture from when we taught this in this course. Okay, so what that's saying is I'm allowed to draw a triangle in quadrant 1, which I've done. I'm also allowed to draw one in quadrant 4, right? This situation exists in quadrant 4 as well. If I do that, I still have an x here, and I still have a 1 here. This is still x squared plus 1. Now, in quadrant 1, the sign of all SIGN of all the trig functions is positive. That's what that A means, right? All my trig functions are positive here. In quadrant 4, cosine's positive, but everything else is negative. Is that true? The way I've drawn this is if this still works. The reason it works is why? This right here is always positive. This is always positive. This guy right here is negative. Even though it's x, we know it can be positive or negative. We kind of, in error, we're used to saying that x is a positive number, but in this case, it is strictly negative, right? So if you do sine, of this theta here, sine of the theta in the picture, you would get what? X over square root of x squared plus 1. Well, we know that's a negative over a positive. Overall, what sine, S-I-G-N, is S-I-N-E. Negative. So quadrant 4 still works because this is, that x value will have a negative sign. Does that make sense? Okay, so what is sine of inverse tan of x? We just found it. That's x over this. We called it, instead of saying inverse tan of x, well, we know inverse tan of x is an angle value or a ratio value? Inverse tan of x. Angle or ratio? Inverse tan of x, the entire thing. Angle or ratio? Angle. So this is sine of the angle. We're calling the angle theta, right? That's what this is? Right? Does this make sense? And I'm not trying to insult your intelligence. We're just going to hit this stuff again in a little bit, and then I think like a couple sections from now, so you need to have some time to look over this. We're going to do a lot of this. Okay, what's next? Limit fun. What is the limit as x approaches 3 from the right of 1 over x minus 3? Okay, we know there's an error, there's a domain issue, right? You plug in 3, you get 0 in the denominator. But if we get really, 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 really close, what happens when you divide by something that's really close to 0? 1 over something that's huge. I'm sorry, 1 over something that's really small, rather. I said it backwards. It's huge. It's either, but is it positive infinity or is it negative infinity? So we know this numerator is positive. If you plug in 3 coming from the right, those are values that are bigger. So you know this is positive and small. So overall, this guy's going to positive infinity, right? Okay. Now, if you think about the graph of tangent, where are the asymptotes? Tangent is what over what? Y equal tangent x is sine x over cosine x. So there will be asymptotes where the denominator is 0, right? Where is cosine equal to 0? Pi over 2, negative pi over 2, 3 pi over 2, all the odd multiples of pi over 2, right? So this is the graph of tangent if I've restricted the domain to just quadrant 1 and 4, right, one time. So this is y equal tangent x. So I know arctan has a similar graph. I just flip everything. Okay. So I want to graph it. I would have asymptotes still, this should be a negative, at pi over 2 and negative pi over 2, but now they're y values, right? Okay. And then my graph goes like this. Do y'all remember this? Okay. So if I have arctan of star, and star's running off to infinity, what y value is this graph approaching? Pi over 2. Okay. So putting it all together, if I have the limit as x approaches 3 from the right of arctan of this part I did earlier, 1 over x minus 3, you see that arctan is still approaching infinity? Yes or no? So what's this answer? 5 over 2. And that may not be as important. Okay, so if I have cosine squared plus sine squared, what is it equal to? 1. To get the other identities with secants and tangents and cosecants, I can divide by one of those trig functions in this formula. So divide all 3 pieces by cosine squared x. What do you get? 1 plus what? 1 plus tangent squared x, not theta, x equals secant squared x. Okay? I don't know that one off the top of my head. I always forget which side has the 1, the tangent, and secant. I do it every time. Okay, so I'm sure you did this also when you did implicit differentiation in Cal 1, but let's just go over it again. If I want to differentiate implicitly with respect to x equal tangent y, left-hand side becomes what when I take a derivative with respect to x? X, the derivative of x with respect to x. Derivative of x with respect to x. Derivative of x with respect to x. 1.
Oh my goodness.
Go back to 3rd grade when you first learned to take derivatives. When you took the derivative of y, you wrote y prime. That was dy dx. When you took the derivative of 3x squared, you just wrote 6x. You didn't write anything else. Right? There was no x prime. Right? It's because the derivative of x with respect to x is 1. Right? So this is 1. Okay. Now, with the derivative of tangent y with respect to x, we take the derivative of tangent, like we would as a function, then we have to multiply by dy dx. Okay? So, what is the derivative of tangent y with respect to x? Secant squared y dy dx. Or y prime. Okay? Either way. I'll switch. It doesn't matter. Okay. So, if I want the derivative of this, just want to solve for dy dx, I would divide both sides by secant squared. So I get 1 over secant squared y, right? Is that true? Okay, so then dy dx is 1 over secant squared y. We go back up a page. How else could we write secant squared y? 1 plus tangent squared y. We have to use the y this time, right? Like that? Is that okay?
Could you leave it as the second one, or do you want to do something else?
Leave it as the second one.
1 over secant squared y. Plug the identity in.
That's what I want to do.
Okay.
Okay. Okay, but I have an issue though, because this is like y prime, and I've got a y over here. Right? Oh, he sees that tan y equals x. So isn't this the same thing as the derivative of y with respect to x is 1 over 1 plus x squared? Or the derivative with respect to x of inverse tan of y, or inverse tan of x rather, right? That's what this is. Was this? Do you remember this from? Got it? Isn't this the same as saying y equals inverse tan of x? We did that in Cal 1, probably very quickly. Garrett? Right? You see it? Okay. So next time we will use this. That's the derivative, so then we'll look at the antiderivative. And we'll do some examples. So notice right here, you look down below this box. If the derivative is this, I just integrated both sides, right? And I end up with this. So next class we will start with looking at this part. Okay?